If you've seen this video and you're thoroughly confused, you're not alone. Fortunately, physics has the answer, the tennis racket theorem. If you fidget like I do, you'll have noticed that some things don't rotate nicely when you try to flip them along certain axes, but they do rotate nicely when flipping them along their other two axes. In fact, there's a rule for this. For any asymmetric object, there's an easy axis, a hard axis, and a middle axis. By easy and hard, I just mean that for the same flipping force, you get more or less rotation speed. Now the question becomes, why does the middle axis not flip nicely? Ultimately, the answer is one of stability. Certain motions are stable under small variations and other motions aren't. But let's look under the hood. The angular equivalent of Newton's second law states that a change in angular momentum with respect to time is equal to the applied torque. Now, when a smartphone or tennis racket is in the air, the applied torque can be treated as zero. So in this case, we simply have that the angular momentum doesn't change, and that means that its derivative with respect to time is zero. Now to unpack that, we use the definition of angular momentum. It's the moment of inertia times the angular velocity. And it's precisely the moment of inertia that tells you what the easy, middle, and hard axes are. In fact, the moment of inertia is a diagonal 3x3 matrix. The first slot tells you how hard it is to rotate around the x-axis, the second the y-axis, and the third the z-axis. Now from a stationary perspective, as the object rotates, those axes rotate, which means the matrix changes. Furthermore, the angular velocity also changes. So a careful examination of how they change implies that these three equations hold. Here we've just labeled I1 as the easy axis, I2 as the middle axis, and I3 as the hard axis, so I1 is less than I2, which is less than I3. The Greek letters that look like W's are omegas, and they tell you how fast the object is rotating around that axis. Finally, the dot over the omega is how quickly that rotation rate changes with time, i.e. angular acceleration. By the way, that careful examination is doing a lot of heavy lifting here, but I won't bore you with the details. Anyway, let's now suppose that the object is initially rotating almost perfectly around the second axis, so that omega 1 and omega 3 are small compared to omega 2, so that the rate of change of omega 2 is also small and can be ignored. Now let's look closer at the angular velocity about the easy axis. To do so, we differentiate the first equation with respect to time and then ignore terms involving the time derivative of omega 2, because it's small. The right-hand side now involves the angular speed about the hard axis, which we have a formula for, so we can substitute. The result is a formula like this. Now this is a differential equation with a known result. In particular, because the right-hand side is positive, it tells you that the angular velocity grows without bound. So the takeaway here is that if an object starts rotating about the middle axis, if it's perturbed just slightly about any other axis, that perturbation will grow because it's unstable. That's why the rotation flips. The perturbation grows so much until it loops back on itself in the opposite orientation, and this only happens for the middle axis. The same analysis for the easy or hard axes imply that the perturbations get smaller, which means that the motion is stable. Happy fidgeting!